Hi class, I am here at home this morning because I am out sick and I wanted to record this introduction lecture for you because I have some old recorded videos that I think will serve us for today, but you guys for sure need an introduction and probably some reassurances about what we're going to do going forward. So in this video, I want to start off by saying that I want you to complete there's two modules for today that I want you to complete. One is for lecture, and it's going to be on the urinary system, and one is for lab, and it's going to be on the reproductive system. The reproductive system part, this is going to be mainly watching a few videos and complete your lab worksheet, like your lab packet that you guys have been working on in labs anyways. For lecture, you're going to have some videos to watch. You're going to want to take notes on those. And these videos are going to seem a little bit fast for you. So in class, when I go over this material, I repeat myself a lot, I draw things on the board, I explain the material a bit slower, but in a video form, I don't think that really lends itself. I think that kind of creates boredom, to be honest. So the video is meant to be really quick, but for you to pause during it. So you'll want to pause, like on every slide, pause once I'm done with the slide, take notes on that slide, and then go on to the next part. So even though the video might be 8 minutes long, you might expect it to take you like 30 minutes to complete it with your note-taking activity during that time. Once you're done with watching and taking notes on those, you're gonna take a quick quiz at the end, and that quiz is gonna take you through the important material in there. And in the module, you can see, you probably already seen, there are learning objectives for this section that you're going to be completing in that quiz. So that is the plan for today. Okay, so with that said, what I want to do next is review with you the parts of the nephron, and you probably remember some of these. I kind of expect that you do from lab. If not, remember last week I said we want to make sure that we memorize the parts of the nephron so that we can learn the physiology really well. If you don't have the parts memorized yet, then you'll want to have them memorized before I see you on Thursday. Okay, so here I'm already starting to draw, and I stopped because I want to go through this as I draw. So here, remember, we call this structure right here, this is the glomerulus, and this is a kind of round ball of capillaries, fenestrated capillaries. They have lots of little pores in their walls, and these allow fluids from our blood to filter into this structure called the nephron. And you might remember this outer part is Bowman's capsule. And the whole entire structure that we have here is called the renal corpuscle. And we briefly went over this last week in lab. Okay, then we also have blood going into the glomerulus. Let's imagine blood is going this way. Is going through the afferent arteriole, and blood coming out of the glomerulus is going through what we would call the efferent arteriole here. And it's important to note that the afferent arteriole typically has a larger diameter than the efferent arteriole. And that's how you're going to distinguish between them in a diagram. The afferent arteriole has a larger diameter and a thicker wall, a little bit thicker layer of smooth muscle in the tunica media in the afferent arteriole. Okay, now as we continue through our nephron, remember this next section we call the proximal convoluted tubule, or the PCT, and then our tubule descends down and back up, in a structure we call the loop of Henle. And we have our descending limb of our loop and our ascending limb of our loop. Then our structure, our tubule is going to coil a bit more at the region we call the distal convoluted tubule, or DCT. And then finally, our nephron connects to a big tube that multiple nephrons actually connect to here. And this big tube is called the collecting duct, which we'll just abbreviate there. Okay, so today we want to focus on what's happening here at the glomerulus and inside the renal corpuscle. And you might remember from lab, and I think you guys went over this with Corey a little bit too, is that filtration takes place in the renal corpuscle, or at the renal corpuscle. And during filtration, remember, large substances are not going to be filtered. So like erythrocytes, leukocytes, platelets, and large proteins in our blood, like clotting factors, those will not be filtered. Okay, these are not filtered at the glomerulus. Instead, they just stay inside the blood vessels here. They stay inside the blood vessels and they leave through the efferent arteriole, and they go into capillaries that travel around this region here. Okay, so large substances are not going to leave the bloodstream and go into the tubule. On the other hand, small substances that are in the bloodstream at the glomerulus, these are going to be filtered out here and make their way into the capsular space, right? The space in here we call the capsular space. And then those small substances will make their way into the PCT and down through the rest of the tubule. And so some of these small substances that are filtered are, let's say, water. See if you can think of some as we go here too. What else is small in our blood plasma? Can you think of any? Let's say water. Urea is a waste. Let's see, glucose. Any ions. Amino acids are pretty small. Ammonia, that's a waste in our blood. Ammonia. Okay. So ions like sodium, calcium, chloride, potassium, those would all be filtered. Okay, so we can get an idea here that not only is water and wastes filtered out of the blood, but also some nutrients are filtered out of the blood, which we started to talk a little bit about last time I saw you in lab. Okay, that's good. Now, I want to share with you a little bit more about what we call filtration pressures. Okay, and if we imagine the glomerulus here, let's draw it like this. There are some slides on this, by the way, in your PowerPoint. I'm just drawing right now because I think it's going to make for like a more, effective educational experience for you. But there are some slides with pictures of this in your PowerPoint. If you want to go and look at that filtration pressure section, you can. There's a really nice slide there on it. Okay, but we can see the structure we have here. This is the renal corpuscle again. And we have, instead of drawing like a really coiled sphere here, this is the glomerulus. I've drawn it differently because I want to be able to write inside of it. So I'm drawing it this way for now. Okay, and we'll call this one the afferent arteriole and this vessel right here, the efferent arteriole. And so one of the things that's really interesting about the glomerulus is that every day, if we take into account the millions of glomeruli we have in both kidneys, okay, remember, this renal corpuscle is a microscopic structure in our kidneys. It's very tiny. And we have millions of these in each kidney. And if we take into account all the fluid that gets filtered through here in one day, we would see that the amount is, about, depending on our body size, okay, it's about 160 to 180 liters. 160 to 180 liters of fluid gets filtered out of here and into the nephron, into this tubule each day. Now, you can imagine we don't even have this much fluid in our body, right? Like, there's no way 160 liters of fluid is in your body or my body. But what happens is the small substances in the blood plasma are filtered through here many times per day. And then as the fluid goes through the tubule, some substances are removed from the tubule and returned to our bloodstream. And so much fluid is returned to our bloodstream. It's actually, about 158 liters of fluid is returned to the bloodstream. And so we only end up urinating about up to 2 liters, right? 1 to 2 liters per day of urine is made. Okay. And so what this means is that, over 99% of the fluid that gets filtered here is going to be reabsorbed back into our bloodstream and taken back into our body. So then that kind of begs the question, well, why filter so much there, right? We're doing a lot of work here just to bring it all back into our blood, or most of it back into our blood. And the reason is we really want to get these wastes out of our bloodstream. We want to get the urea, the uric acid, the ammonia, creatinine, wastes that our body doesn't need. We want to remove those, and we want to be thorough about it. We also want to remove toxins, medications, things that don't belong in our blood. So we want to have a very robust filtration process here, and then return only what we need to our bloodstream. And the other neat thing about this, and you might relate to this, is how when you clean out your closet, the best way to clean out your closet is to take all your clothes and everything out of your closet and then only put the things back in that you really need. If you were to just look in your closet and take out, look for things that you don't really want anymore, you probably wouldn't take much out of your closet. But if you take everything out and only put things back in that you need, you would clean out a bit more. And that's what we're doing here with the fluid in the blood. We're taking so much fluid out of the blood, then we're just going to return what we need to the bloodstream later. The rest that's waste will just stay in the tube and end up in the urine eventually. Okay, so let's talk about then, how do we get this huge amount of filtration going on here, right? We have so much filtration happening here. And this is where our filtration pressures come into play. So I want you to know that there are three filtration pressures, and I'm going to erase a little bit because I have way too many lines on here. Okay, so we have 3 important filtration pressures that we need to consider, and this will set us up for you guys to watch the other videos. Okay. All right, so our first pressure we need to consider is called our glomerular hydrostatic pressure. We often call it GHP, glomerular hydrostatic pressure. And this is the pressure from the blood inside these capillaries here, inside the glomerular capillaries, pushing out on the walls of the capillaries. And you might remember back from, I think it was chapter 21 when you guys did blood vessels, that capillary hydrostatic pressure, right, or blood hydrostatic pressure. This is the force of blood inside blood vessels pushing out on the walls of blood vessels. This is the same concept, but we're just calling it by the name glomerular hydrostatic pressure because we're in the glomerulus today. Okay, so this is really just the force of blood. Because blood is trapped inside of these blood vessels, right, it's going to push out on the walls of the vessels. All fluids do this. Whatever container they're in, they push out on the walls of that container. So that's the force of the blood pushing out, the GHP. And in a typical capillary bed, this capillary hydrostatic pressure would be around 30 to 35 millimeters of mercury. But here in the glomerulus, it is going to be, and I would like you to memorize this number, it's going to be 55 millimeters of mercury. And this is a very high capillary hydrostatic pressure. The reason it's so high is because of these arterioles that we have here and here. Okay. Notice our afferent arteriole has a very large diameter, right? It has this very large diameter here. So it's letting a lot of fluid in to the glomerulus. And our efferent arteriole has a very narrow diameter. So it's just letting like a little bit of fluid out of the glomerulus. And so this creates like a bottleneck effect, similar to what you might see like on a highway that goes down from like 3 lanes down to 1 lane, right? Where all the cars have to fit into this one single lane. And so traffic slows down there and the pressure goes up behind that constriction point. It's the same idea here. We have a big inlet and a small outlet. And so the pressure inside these capillaries really builds up to 55 millimeters of mercury. Now, this is going to be our main driving force for fluid moving out here. So I really want you to memorize this pressure. This is a really important one. Now, our second pressure that we need to consider is called our capsular hydrostatic pressure, or CHP. Okay, and this pressure is the pressure of so we can imagine, right, some fluid has been coming out here into the capsular space, and that fluid is collecting out here in the capsular space. This fluid, we call it now filtrate, right? It used to be all that small stuff in our blood, but now it's out here. It's like some water, right? Glucose, we said, ions, urea, different small substances. And these substances are there in this fluid, and this fluid is going to exert some pressure back on these vessels. It's also going to exert pressure out here on Bowman's capsule, and it's going to exert pressure in this direction too, right, going into the PCT. So this fluid, because it is pushing out into the PCT, it doesn't push back that hard on the glomerular capillaries. It's kind of a weak pressure. And to be honest, at this moment, I can't remember the exact value. You don't need to remember it either. Let me think about this. Why can't I remember? I want to say it's something around like 18, maybe 15 millimeters of mercury. Let's say it's approximately 18 millimeters of mercury. Oh, I wish I could remember the exact value. That's okay. All right, so that is our capsular hydrostatic pressure. And I just want you to notice that it is opposing the glomerular hydrostatic pressure. So this force, this capsular hydrostatic pressure, since it pushes back in, right, it's fighting against the glomerular hydrostatic pressure. So if we were going to calculate like the net pressure based on these two competing pressures, we would subtract them. Does that make sense? We would subtract 55 minus 18 to get like our total pressure at this point. Okay, now we have one more pressure, pressure number 3. And oh gosh, let's see if I can remember what this one is. Oh, you guys probably remember this one from back in chapter 21. This one is called our blood colloid osmotic pressure. How could I forget this one? This one is such a fan favorite, if you will. Okay, so BCOP, B cop. Okay, so our blood colloid osmotic pressure, you might remember back from chapter 21, this pressure is due to, let's kind of zoom in here a little bit. This is due to the presence of proteins that are trapped in our bloodstream. And remember, proteins, they have lots of negative charges associated with them. They're very hydrophilic. So they have this like attractive force where they pull water from other compartments in the body toward them. So they kind of draw water this way into they have a tendency, these proteins have a tendency to draw water into the glomerulus, into the glomerular capillaries. And so this pressure, B cop, is just like it is everywhere else in the body, approximately 28 millimeters of mercury. And it's just due to the concentration of proteins in our blood, because the proteins attract water. And so they draw water from the capsular space and try to get it to come back into the capillaries. So notice this pressure, B cop, is also opposing the hydrostatic pressure here. So both capsular hydrostatic pressure and B cop, these oppose filtration. And so if we were going to calculate then our total pressure, we would take our 55, our net filtration pressure or total pressure. We're going to take our 55 millimeters of mercury and we're going to subtract from that the sum of the other two, because these two are working in the same direction. So we're going to then have 18 plus 28. I really hope that's 18. Let's see how the math works out. All right, and remember both of these values are also in millimeters of mercury. Okay. And so let's see, what's 18 plus 28? Okay, 18 plus 28. 46. Okay, so in the end, we're going to have 55 minus 46. And that's great. Okay, 55 minus 46 is 9. All right, and truthfully, this number should have come out to 10. So I must have been one off in one of my pressures somewhere, or maybe two off in certain pressures, but it doesn't matter. 9 is close enough. We get the point. Okay, and so in the end, we see that filtration wins over reabsorption, or like pressure pushing out of the glomerulus wins over pressure pushing back in to the glomerulus by a force of 9 millimeters of mercury. Okay, so this is going to be our net filtration pressure. And so all the time in your body, we have this force of fluid pushing out here in sum, okay? And remember, this is due to that really, really high glomerular hydrostatic pressure. Now, this is important because remember, we have to be filtering our blood all the time because we need to get the waste out of it. We need to get the urea out, the ammonia out. So this has to be consistent in our body. We always have to have that net filtration pressure of around 9 or 10 millimeters of mercury. Now, there are times in our body where this number can fluctuate. Like, let's imagine we have maybe high blood pressure. Maybe we have hypertension, okay? And this 55 millimeters of mercury, right, this glomerular hydrostatic pressure, it gets a little bit too high. Maybe with our hypertension, it's 65 or 75 or 85 millimeters of mercury. That would put our net filtration pressure up to, maybe 20 or 30 millimeters of mercury. And what that would do is put a bunch of force here on this membrane and cause fluid to flow out here very dramatically, okay, and through the nephron very dramatically, lots and lots of fluid leaving. And it would cause us to make extra urine and urinate a lot. This person might notice they're urinating twice as much in a day as typically someone would. And they would become very dehydrated. So let's say if the glomerular filtration pressure, or we could even just say the net filtration pressure. Net filtration pressure is too high. Okay. We could say our glomerular filtration rate, or GFR, is too high. If we're filtering fluid at this glomerulus too fast, then we would become dehydrated. Dehydration would occur. And conversely, let's imagine maybe our blood pressure is really low, maybe we're very already dehydrated, and instead of having a glomerular hydrostatic pressure of 55 millimeters of mercury, like we have here, it's just 45 millimeters of mercury. Let's imagine it's just 45. Then when we do this calculation, we would get a net filtration pressure of around 0 millimeters of mercury. And that would cause our glomerular filtration rate to be 0, right? We wouldn't be filtering at all. So let's say if GFR, our glomerular filtration rate, is too low, wastes will build up in our blood. So if our GFR is too low, wastes will build up in the blood. This is a big problem because those toxic wastes like urea and ammonia, they will cause a condition called azotemia. Azotemia is a high concentration of nitrogenous wastes in our blood. And these wastes can become toxic to us, and they can cause death as a result. So this is a major concern. So you can imagine every day our body is trying to stay right around this 9 millimeters of mercury, giving us that glomerular filtration rate of, what did we say it was? We said originally it was about 160 liters of filtrate per day. Okay. And our body tries really hard to maintain this. So let's say GFR must stay stable, because we know the consequences if it doesn't, right? If GFR is too high, we'll get dehydration. And if GFR is too low, waste will build up in our blood. So it's really important that GFR stays stable. To do this, we have 3 categories of mechanisms to regulate the GFR. We have 3 categories of mechanisms to regulate GFR. We have where the kidneys regulate themselves, renal autoregulation. Okay. We have neural regulation, where the brain regulates the glomerular filtration rate. And we have hormonal regulation, where we have hormones that regulate the filtration rate. And so the next video that you're going to watch is going to take you into these 3 mechanisms. So I want you to continue on there. Okay. And in the video, it says something at there in some point about like that we covered this in class last time. We did not cover this before. This is a video from a few years ago. So that's why I had mentioned that in the video, but that's not true in our case. Okay, so this will be new for you. So remember to pause the video and take notes. The last thing I want to mention before I wrap up here is that so far we've been drawing our nephron looking like this. And you guys are familiar with this structure. In reality, our nephron is actually a little bit more condensed looking than this. And so I want to draw you that version now so that you can be familiar with that as you go into the next video. So typically, here's our glomerulus, here's our arterioles, and typically our nephron, so here's our Bowman's capsule. And I'm just gonna fuse that together and draw one line for the PCT. So normally the PCT is really large and coiled, okay? It's really long. And then the loop goes straight down, and it's gonna be, actually the loop is gonna be extremely long in the kidney. It's gonna go all the way down into the renal pyramid and back up. And the loop is gonna end right here by the afferent and efferent arterioles. It usually like crosses behind, let's say here in this case, the afferent and efferent arterioles. And then we have the DCT coiled up here. And then we would have our collecting duct. And so let's make the collecting duct like a thicker line. Okay, maybe the collecting duct runs through the background here. Whoops. Runs through the background. But this nephron is connecting to the collecting duct, maybe here, okay, right in here. And then we would have multiple nephrons connecting to this collecting duct. Okay, so we would have like another nephron over on this side, right, coiled up over here, another nephron over here with its own glomerulus, another nephron over here with its own glomerulus. So you could kind of get the idea. But what I really want to show you is that instead of our nephron being very stretched out, right, very elongated like we see in this picture here, the nephron is actually very, very condensed. See how it all like fits in this area essentially. And very importantly, the end of the loop is going to pass right next to the afferent and efferent arterioles. This anatomy is important for you to understand as you go into the next video, where you're going to look at the autoregulation of the glomerular filtration rate. Okay. All right. I hope you have a great day. I will see you hopefully on Thursday if I am feeling 100%. And I will talk to you soon. Feel free to email me if you have any questions.